you look at this, you can get some good bit of information, get yourself familiar with it. You notice when you do at least get the statistical variance of certain numerical columns, obviously you're not going to get that for the categorical columns. So for that, we can do things such as just plot out the values. So, I knew I hit something. Probably come back to that. Let's plot out a histogram. Oh, crap. That's going to take a while. But I've done it elsewhere too. Let's, for that department column, which had different values, well, what's the value distribution? This is a nice, single line code. Okay, we'll come back up. Single line code that shows you here's what it is. Again, for all of the other numerical fields, here's the distribution raw form. We haven't standardized, normalized, none of that. This is what the numbers are, right? So as you can see, here, and the salary, high, medium, low. The majority of people are classified as having low salary, medium, and very few high. I wonder why that is. Smoker, are they a smoker, yes or no? But then when you look at the numbers, it's kind of low. I thought we had 15,000. What's going on? Something worth digging deeper into. There are interesting packages in R, Python that do all of this sort of stuff, descriptive statistical stuff, that are freely available. Everyone will have their preference on which ones they like. One that I like is called Pandas Profiling. And when I run that, that gives me a lovely little report. We're going to go back and up and down on this for a little bit. As you can see, it gives me a nice little report with all of the raw statistical information, distribution, all that I want to know about the data to get myself intimately familiar with this data set. Okay? So we saw things such as missing values. That is smoker. 98.4% of the columns have missing values. That's not good. And then we've got two other columns. Time spent the company. That's important. We know that's going to be important. That's got 1% missing. And average monthly hours, 2.5% missing. We're going to have to do something about that. It also says, hey, data set has 2,740 duplicate rows. Is that normal? Well, the kind of data that this is it possible that there may be multiple people who have similar characteristics? Not all of them as 2,000. It's like 2 people might have similar characteristics based on the type of data columns that we have. The answer is yes. So we can say, let's not be concerned about the duplicates. So we see all this. So now that we know a good bit about this data, and I know this is laborious, but I need you guys to get familiar with this data set too with me, because it's going to be important. Correlations. How are one column correlated with another column? And you can kind of see a score for that. Inversely correlated to positively correlated between the colors ranging from blue to red. And you can begin to see such as number of project seems to be somewhat correlated with last evaluation. Here's a nice deep red one. Average monthly hours with number of project. Obvious. Right? Duh. And so on. This stuff is really useful. And to build these sorts of correlation plots are actually like one line in R and Python. Here you go. This stuff, and so you can use fancy software to do this descriptive analysis, or the reason why a lot of data scientists prefer this command line Python, R, is because they just write one line and here you got it, right? It's efficiency. It's like a true programmer will never take their fingers off of the keyboard. They won't use a mouse because they know all the keyboard shortcuts. That's what this stuff is. You want to do this over and over so you can get faster at it, better at it. The more you do, the more practice you get, the better you get just doing this. That's where you got to spend the time. So Here's a sample. Great. So we're done with that. So let's move on. We need to do some feature engineering. Right off is smoker, a lot of missing values. What do you guys want to do with that column? This is smoker. It had, what, 90+% missing.
Discard it?
Discard it. Anybody second that or have another idea? Sold. We're going to discard it. So just get rid of it. And here, one line that says, give me a percentage of which of these columns have null missing values. And as you can see, is smoker was 98.5%. Yeah, we want to discard it, and then we have these two other columns that we got to figure something. So just one line on that. Yes.
You don't have to check the value of the smoker data before discarding. That might be the perfect predictor. You don't know, right?
That is true. That is absolutely true. We don't know. But when you have to make some of these choices quickly, and we're going to see a couple of things that can help later. Right now, you're just going by the choice of whether or not discard based on the fact that it's missing. You look at this categorical, this little description column here, and you look at that correlation plot. Where is smoker?
Another question over here.
Yeah.
So I'm looking at new conversion for everything but instead of sign. So I'm just wondering, like, what's a good rule of thumb, like, you know, just to wing it, that you would basically discard a column based on how much missing data you have. And in this case, it's pretty obvious because 98% is like but you know, is 70 a good limit, or what do you usually use in this sort of scenario? Like in terms of how much data you're missing?
I'll answer for myself because I don't know what the standard practice is. I don't have one. I literally will just look at like what proportion is this? What is this column? Is smoker? And when you think about if a guy's gonna leave, a guy or gal's gonna leave, knowing whether or not that person's a smoker, is that important? And I know that this data column is troublesome. I will say, I will work iteratively, is my answer. So the first pass of building this solution, I will say, I don't have the time to figure out a way to deal with all that missing value, so I'm just gonna bench it. I'm just gonna throw it away for now. And I know that I am throwing it away. The next iteration, the next pass I do of improving my model, I can say, I have thrown that column out, let me go try to fix that. Let me see if there's a way that I can backfill that data. And we're gonna do one of those backfills. Does that answer your question? You're very welcome. Great question. All right, so where were we? We got rid of one column. The next one, time spent the company, which had 1% missing values. For that, what we're doing over here, let's dig in a little bit further. That's one column. Is that correlated with something? Let's look over here. Time spent the company. Is that correlated with anything? Obviously not by itself, but anything else. Looks like number of projects. Time spent the company and number of projects. There's this. It's a little deep red. So why don't we plot number of projects against average monthly hours? Was that one we looked at? Number of projects, average monthly hours, number of projects. So you kind of look at correlation plots like this, and you make a judgment call to what are we going to look at. So here's what we did over here. You build a box plot for splitting out the number of projects and plot out average monthly hours. I hope this is visually intuitive. We just took two of the columns, and we just tried to plot it out. So we took average monthly hours, and that'll be whatever, right? Well, let's split that, bucket that by number of projects. And you kind of begin to see this sort of distribution. Well, this is nice. What does it tell you? Yes.
I assume the number of projects is the number of projects over the entire time of the window. Or is
question.
or is it per year?
Good question.
It says monthly hours.
The monthly hours, that says monthly hours. The question is, this column here, is this for projects concurrent? Or is this the number of unique projects that that person has done over their tenure in the company? Don't know. Excellent question. I don't know. That's a question that I should know if I'm trying to get intimately familiar with the data.
And the monthly hours also is the average over the whole career.
Presumably, again, I don't know exactly whether that would be the last 6 months or if it's somehow they track their hours, which for something like average monthly hours, that would be for the whole tenure. If you've got a time clocking system or something, or if you work with billable hours, you're a law firm or so on, that's an easy number metric to get for all employees. Great questions. Thank you. Oh, go ahead.
Is there typically a document that goes along with the data set that you get that specifies a lot of this? Or do you just have to dig it out?
In the real world,
Right.
oh God, I've done 30 plus engagements. I've never,
Okay,
ever.
so you just have to dig it out.
You dig it out.
Okay.
So you sit down, for me as a consultant, I will have to sit down with folks from IT. I'll sit down with folks from operations. I'll spend folks in the nursing clinical side and so on. Work with them, help them tell you what's important. Then you go back, they'll collect the data. Then you go back to them in weekly meetings or so on, which you try to put in their calendar, and do some descriptive analysis, and you say, hey, I'm seeing these patterns, what does this mean?
Right.
And you have this sort of dialogue with the domain experts, so you two become at least somewhat qualified to work in their domain. Not an expert, but do the best you can to understand the data. Excellent question, thank you. Anyone else? I think we're making good time. So we see this, and we can see that there is a distinct pattern for the number of hours that's different. It's not going to be more or less uniform. So to fill in the missing fields for average monthly hours, what we can do is we can take the average of each by number of project, which is what we do right here. 2 lines of code. And that gives you a dictionary in Python that says for those who work 2 projects, 3 projects, 4 projects, what's the average number of hours for those that you actually have data for. So now, for those fields that have that missing, go ahead and fill it in with that average based on the number of projects. Yes, sir?
There's always this confusion about mean, median, and mode.
Great question. The question is mean, median, and mode. Mean and median are common ones. Mean is average. Median is, for all the data that I have, I just took the 50% down. That 50%, the halfway mark, right? You can go with, it depends on the situation and the distribution of your data that will mathematically dictate your choice to say, why would you go with an average or a mean versus a median? And that would, ideally it's okay to pick a median if your data is normally distributed. And even though, and you need to know what the standard deviation is and so on, then you're already calculating the mean, but even in there, even though you're looking at this data, and you know what it's normally distributed by around the mean and so on, you can still pick the median because you know that the data reflects something. You're looking at some kind of time series or something, so you can say, I'll take the median point there, because that makes relevant sense to the model that I've conjured up in my head. Mode is not really used as much. I don't think I've ever really used a mode. Does that help? This case, I'm trying to pick, because I'm already guessing a number, and I'm giving it to them. Average for a block of people that are similar to the person who I'm backfilling, the average feels right. I can't believe I just used that word. Very data-driven, feels right than using a median.
I think if you have a lot of outlines, kind of outlines, you don't want to use an outline. They're susceptible to
That will, exactly, thank you.
skewness.
Thank you, that's an important point. If you have a lot of outliers, the outliers are going to skew your average. That's the reason why. Thank you.
You guys compare different methods for doing the mean values, or just you're gonna stick with this one?
We're going to stick with this one, just this one.
Does this include those who have left and those who are working? Or
Correct. That's why we have yes and no's. So that's why we have those who have left, small portion, and no's, they're still with the company. And the idea is you're taking a snapshot in time, a picture of this company, and based on some of those characteristics that we saw, those columns of information, it's not comprehensive. It doesn't give you their age. It doesn't give you their address. It doesn't give you certain other things that are, it doesn't tell you their gender. Gender is also predictive of whether somebody's going to leave in the future and how quickly they leave. So those sorts of things you don't have. You don't have everything, you just have just that. And using only that, we have to try to build a model that predicts.
does this include everyone who's at the company currently or just 5 years?
You presume it's 14 and a half, 1 minus 15,000. So that would be, we figure that's a medium-sized company. Yes.
You have a small minority class, a large minority class. Do you upsample it? So
If-
you don't, get.
Very good point. We're going to do a little bit of dimensional reduction where we're going to do some of that. The question was, if I have different classes and they're imbalanced, do we upsample? So basically it says you want to even out that plot that I had. You can kind of see the sizes, even though this gives you a range, the sizes vary. So are you going to try to get particular metrics where we just computed based on saying, forcing these buckets to be similar? You can, that's being very precise.
Just adding on to that question, that it's more about the target variable. So say your target variable here is churn.
Mhm.
When you're building your training data set,
Mhm.
would you recommend building a balanced data set for across
50%.
all customers? Meaning, not customers, across all employees in this case. Meaning, say you have different segments of employees, different departments as you mentioned. And you want to build a data set which is not representative of the data set population that you have, but balanced across all departments in terms of churn and not churn.
Excellent
Would you
question.
recommend that, or would you say that depends on the scenario?
It depends on the scenario. Commentary. This is just my opinion. In the old days, we actually did that. Last decade, when I had to do some of this, I did do that. But I never felt comfortable doing that because what I felt that I was doing was I was artificially engineering real-world data to fit certain normalized patterns. If I'm trying to build a predictive model that is going to try to predict off of the real world, I want that data set to be unadulterated as much as possible. That's just my view. When we look at things such as we're building these auto machine learning functions, when I throw in data, I'm going to throw in not that process data set where I've taken out is smoker. I'm going to leave that in there. Because I want it to figure out what that column had so much missing data. Is it useful? And then I'm still going to measure its performance at the bottom line. How well did it do? I looked at the data, I could see is smoker has got a lot of missing values, and I'm going to toss that out, I'm going to try to build a predictive model, and I'm going to measure its accuracy. What's the kind of accuracy that an automated machine learning function? So if you're going to build tools like that, they're going to be working off of real world data too. They may kind of balance, and there's certain features like rapid miner, and we'll see that in the interface. It says, do you want to balance this? Yes or no? Just click a button and it'll do that. You can do it, and then you look at the performance. You look at what kind of predictive function you get. And does that jive with reality?
But if you want to get actuality, you have to take the dirty data out of there, right?
You're pre-processing, so you hope that that process of taking out the part of the data that's dirty is standard. So you're going to have to do that all the time.
But your AI function, you're going to input in there a parameter to say take out that data so that you can have accurate statistical information. Because humans make errors, the data could come from all kinds of stuff, hiccups and whatever, right?
The question is, this is important, how much of that pre-processing do we really do, especially with artificial intelligence? Here's the beauty of it. What those models are doing, what those tools are doing is they're not running the model once. They are running what we're going to do once, they're running that recursively thousands of times. And then it sort of rank orders all of them and says, this one seems to has the highest performance, so this is the one I'm going to serve up to you. So if we could do that, but then we'd be manually doing the same thing many, many times, and looking at the output of the model, it just take a lot of time. And so when we put our faith in these auto functions, we are saying, you figure that out. And I'm going to trust that judgment, that autonomous, process-driven judgment. That helps. Great question. Let's move forward quickly. So we've filled in the values, and the other was the third. Oh, just those two. I mean, exactly is. So now, if we look at, are there any NAs? Nope. They all seem to be pretty fine. Here's the test. We're just doing an equal sort of logical test. Are there any nulls? And it should say, oh, because I changed this data set. But it should be true. It worked. And here it is. Distribution. The one other thing we can do, remember we had categorical features for department and salary. There is a process called one-hot encoding. And that just basically means take the different categories like salary, high, medium, low. Let's take that one column and split it up into 3 columns, high, medium, low. And they get a yes or no on those for the appropriate value. So for the 3 salaries, if the salary is a high, then for high, medium, low, the values would be high, yes, 1, 0, and 0 for medium and low. Right? That's all we do. One-line command in pandas says called get dummies, and that gives you the one-hot encoding. And when you run that, I don't want to mess this up because I've altered the HR data table, but you can see here is what it did with department. It split out department into department ID, department R&D, accounting, so on. Same with salary, high, medium, low. And if we look at the data, as you can see, it's one hot encoded, 0, 0, 0, 0, 0, department sales, first person's in sales. And remember, sales have the widest proportion, so a lot of them are going to be in sales. And same with salary. This person's salary is low, not high or medium. Okay, so that's all we've done. And I've got that process file that I've saved. So now, this is going to get into a little bit of mundane statistics. I ask you to bear with me. But ask questions, please. We're going to try to do a little bit sort of modeling with all of this data. We're not doing machine learning quite yet. We're still sort of playing with the data and visualizing and getting a sense for what fits. Okay? So the first thing we'll do is what's called a bivariate graph, and that's taking a look at two of those variables that we know were pretty strong red in that correlation map and so on, last evaluation and satisfaction level, and layer it on the left value. And so you begin to see, and this sort of just shows, at least for this, just the correlation between them. We're going to do the layer on layer. But in this one, you can kind of see between these two values where there's a lot of like correlation, commonality, right? That's nice. Let's go on to layer in the left variable. And you get something like this, where it gives you a heat map that says for those zeros and ones, whether the person left or not, for last evaluation and satisfaction level, there's a concentration around here. Now, what is this lovely little piece of artwork? What does this tell me? Well, let's build a similar artwork for something else, like average monthly hours and number of projects. The same thing with like, you know, the shading red or blue, and the intensity of the correlation based on like how red or how blue. Let's do that instead of for last evaluation and satisfaction level, let's do that for average monthly hours and number of projects. Looks awful. There's no pattern to it. Like here's the blue, which is for, yeah, they left, but it's over here and it doesn't seem to overlap.
I've got a quick question. So this is a really interesting plot, but it looks like you're plotting first the red distribution element, and then you're plotting the blue distribution on top of that. Mm-hmm. In which case it looks as though the blue is occluding the red. So like you can't tell that big blue spot at the bottom left.
Yes.
You don't know if there's also a big red spot
underneath it.
So do you know of any quick and dirty ways to try to do the same thing without this occlusion problem?
I'd have to hit the books, yes. There are several different ways. There are several tools that help you visualize the data, and that's a subset art form of data visualization. And a lot of times, you don't have to do machine learning. By visualizing the data appropriately, you'll identify the trend and pattern that tells you exactly what you need to know. Your predictive model will come from appropriate visualization. This one does not do a good job, but there are great visualization tools that are built into Tableau, Microsoft Power BI, and so on, and all sorts of visualization packages out there. There are different plots and so on, diagrams that are just there. That you just can try to plot that and you can see it. Great question, thank you. All right, so this was nice. At this point, do we feel like we've gotten a sense for the data? We know the columns, we get it, right? Let's switch to RapidMiner. I promised you would, oh, it crashed on me, I forgot. Stupid program. Better run. And then we're going to do this because I know that it takes about 30 minutes or so. Now this is the easy stuff. Come on. I was having a Twitter exchange with a guy who founded this, Dr. Ingo Mirswa. His PhD thesis work was on feature engineering and sort of this automated feature engineering. And he was, as he founded RapidMiner, he incorporated his thesis work into the RapidMiner tool. And so what he does here is new process, start with a blank.
It's right here in the corner, I think.
Is it in the corner?
Left front.
Thank you. Thank you so much. Me. Why does it? Okay, RapidMiner, these guys need better software engineers. Okay, so what I already did, should be my local repository, data. I loaded this HR table. This was exactly as we had it. If we were to go into design, and again, we talked a lot about tools to visualize and so on. A tool like RapidMiner, as expensive as it is, of course, will also have great ways to get statistics and charts and advanced charts to be able to help you visualize and understand the data, right? This is not a RapidMiner class, so we're going to ignore that. We're going to go into its auto model. So taking that data, we want to predict. We don't want to do a clustering or outliers. We want to predict this left. And mind you, we only have the raw data set, and does this have is smoker? Oh, what I did was when I added it in, you'll believe me if I show you. Let's import new data. HR data. And over here, is smoker is here, right? So let's drop is smoker. Let's make sure left is a categorical variable. Final one. And let's exclude is smoker. Ingest, we'll put it here, we'll just call it HR data, finished, and it's done. It's all here, right? So what we want to do is predict on left, and it tells you here's the distribution. Do you want to map the classes to new values, or blah, blah, blah? Which class is of highest interest? The yes, we're interested in the yes. That's important because it's going to do some feature engineering. We're going to see what those new features that it concocts are going to be. It does say things such as, this is pretty cool, correlations. What looks like an ID, like a social security number. It would recognize that and say, that kind of feels like an ID, and it gives me a high score. Things such as stability and missing. And as you can see here, average monthly hours, 2.45% missing, and so on. For average monthly hours, 1% missing, and we dropped is smoker. So let's go with select all. Selected all of that, and here's the automatic feature selection where it will construct new features, and yes, it will take a long time. I don't want it to be too accurate, I'll just do a balance between simple and accurate, and I'll have it generate some new features. And then I can do all of this. And that's it. Naive Bayes that's quick. Let's do them all. We're going to be doing SVMs, but I'm going to ignore it for now. SVMs take too long. And they're not done. And it is running. And this is it. So, and let it run. It's going to take up a lot of my computational power on my machine. We're just going to let this run. And we're going to come back to it, and you're going to see things such as ROC, repeat operator curves. It'll plot that, so you can get a sense for the AUC, right? For all the different these models that we've selected. And then for each of them, it'll give you like the model, simulator, performance metrics, blah, blah, blah. We'll get all of that too. And we'll come back to this when it finishes, right?
Is it gonna do cross-validation or split the data and training?
Everything. Oh, it'll do everything. That's the whole automatic. And I'll
I
drive
want
it.
to for the metrics. So when you see the accuracy, it's going to be on 20% of the data or just the average?
Let's take a look. One of them's done. So here it is. Here is the accuracy, and if we look at the specific model, and you can see by specific, it can split it. You asked me if it did a cross-validation. Well, yeah, it would have to have done a cross-validation if it needed to get this sort of metrics. And so this is for the naive Bayes model. If you go back, naive Bayes got an accuracy of 87%. Okay, keep that in mind. Just keep that in mind because we're going to be building things manually. We'll see what kind of accuracy we get. Okay, but there are all these cool stats that you can get. Let's go back to our very manual caveman world where we code this slowly. All right, let's split into training and test sets. If does anybody have a question like what percentage do you use for test and training or validation as well? It's up to you.
You should use the same that RapidMiner is using, right? Because we are going to compare the results.
No,
similar
because
to that.
we're comparing not just the results. Good question. Should we use the same kind of split that RapidMiner will use? No, because we're testing performance and process overall. We're not trying to mimic what RapidMiner or H2O will do. We're trying to say, if you're going to be autonomous, then you're a robot. You do everything on your own. I don't want any hints of what you're doing, and I'm not going to give you any hints of what I'm doing. That's why we dropped is smoker, but ideally we would have left it.
Yeah, but we're going to compare the results. Yeah.
We want to.
You have to use the same test situation, example, right?
Yes, you can certainly, yes, you can do that. You could, absolutely. Yeah, if you hold my feet to the fire, yes, I think the answer would be yes, you would. But again, here's what we're going to try to do. We're going to try to build a model. And you'll see that at the very end, when we publish that trained model, we're really going to go back and use 100% of the full data set and take the model specifications, the coefficient weights on all 100%. Because when the training and split that you do is really intended to help you identify one of a plethora of different algorithms that you want to say, this is the one I want, and call it as my predictive model. And here are the hyperparameters. Here are the weights and whatnot that I want to use for that algorithm. That's my model, really, right? And so that's all the split itself is a discretionary step when you think about it philosophically.
I think the other thing to call out is the difference is obviously the tool can do multiple iterations of cross-validation by cutting it separately, like the cable.
10 times, 10 folds, 20 folds.
Exactly. Versus when you're doing it manually, you're going to do it once.
Correct. TensorFlow 2.0 from Google, when it comes out, it's built in, when it does its cross-validation, it does that even recursively.
Right.
And all of this is possible because we're those who build it assume that we're going to live in a world of extreme computational power. So why not use it?
What do you mean by recursively cross-validation?
Sorry?
What do you mean by recursively cross-validation?
Oh, what I mean by doing it 10 folds, 20 folds, 100 folds, 200 folds, and so on. And then trying to get the right performance overall of that. And then picking, okay, this one did well. So it looks like 100 folds gives you the right performance. That's what I mean by recursively. Yes, sir.
I mean, going again on the same topic, I understand the point, but for me, if you want to compare apples to apples, so if RapidMiner is doing like, I don't know, 5-fold cross-validation or 10-fold, whatever, why are not, you should do it here, or it would be good to do it as well. It's just same line of code.
Next iteration. I'm going to note that down. Next iteration. Next time I do this, I'll make sure, yes, so you're right. It's not going to be a perfect comparison. Like I said, if you kind of hold my feet to the fire, I cave on that. Yes, you're absolutely right. All right, so let's do that. I'm going to set the seed 42. That's just me. Reference to that stupid movie, Hitchhiker's Guide to the Galaxy. Number 42 is the answer to everything in the universe. Okay, so one of the things, in order to do support vector machines and k-nearest neighbors, you want to standardize your numeric columns. And so here's the function for doing standard scalar. Go ahead and do that. And so we're going to try to fit our first support vector machine classifier. And it's just this, using scikit-learn, right? Takes a minute or two, and it's built it. And so now you take that model called SVM, and you predict it with the test set, that 15% holdout. What's the accuracy that we get? 76.4%. Remember, the naive Bayes was a little bit better, but this is a support vector machine classifier. Very simple. It's a starting point, right? So is there anything we can do? Well, if you read the manuals for SVCs or vector classifiers, if you try to understand the mathematics behind it, it uses a kernel. There's a trick that they use where they call it RBF, and it is not boosted decision tree or anything. It is a, thank you, rapid, what is it? Radial basis function. There we go. Radial basis function. I did look it up and put it in my notes here somewhere. So let's do that. Did I pull that here?
Instead of linear.
Oh, this is just a terrible. Okay, so what we're doing here is now we're actually trying to fit it. We're still stuck with that original model. We haven't done the RBF yet. We try to fit it to see what does it predict, and it says 100% nobody's left. And let's try to use, there's another package called MLX10. Let's try to depict that graphically. What does that look like? You know, the blue versus the red or orange or something. Takes a little while. These are older packages. We are actually using technology that was available more than 10 years ago. All right? And what do we see? That 100%, this entire shaded blue. So obviously this accuracy of, in the predictive model of 76.4% ultimately isn't even something that we can operationalize, because it'll just say, when you do operationalize it, it'll just say, yeah, nobody leaves. That's helpful. Doesn't do anything. Okay? So the RBF is radial basis function. Thank you, the kernel trick. So let's run that. And you get the accuracy of 90% now with that RBF for that SVC. Now, what's the difference? One was the first one that we did by default was a linear function. The RBF is a nonlinear, right? And so obviously nonlinear will do better. So is there a way that we can kind of get the confusion matrix for this? Yes. And we get to, let's do a fit. I'm going to move very, very quickly. That same thing we looked at, where we looked at like how many of it did it predict, and this is going to try to put it into a nice little picture. Come on. Still running. And I apologize, even when I did this at home, I have to be careful because my processors are being used by RapidMiner. So even my machine's going to be a little slow. So I guess I may not be rerunning any of it, much of the code.
Sir?
Go ahead.
That first, those two results that you just ran, the one, specifically the one that's 90% approximately.
Yeah.
Right. So I guess this is a question similar to the one I had before. Why would you not think that the model didn't overtrain to memorize data based on the training basic?
Whether the model overtrains, it's basically when you get performance that's really, really good, and then you have, even on the test set, it seems to do well. If it does better than what you expect, you're overtraining, overfitting. You've got a model that overfits. And then you have to test even more, which is why in a lot of deep learning methods, they don't do the test train split. They do the test, the train, validation, and then a separate test split. The idea is you train a model, then you look at the validation split. So say you go 70% train, 15% validation, and then another final 15% for the test, unseen. You train with the 70%. then you use the 15% for the validation set to improve the hyperparameters for your selected model.
So you, basically, it's too early to say that it's.
Use that to fine tune. And then you test it. So we're going to see that. We're going to do that in H2O. Excellent question. So here it is, an RBF kernel. We saw the picture earlier. This one looks nice. This one looks better. So that's great with an SVC. Let's go ahead and build a K nearest neighbors.
There is another parameter in the SVN that is really important, is the C.
Say
We are
that.
using C equal 1 there all the time. So I think, you can also do grid search on
I
that
can
parameter.
do
and
grid search,
write
yes.
those
You can,
parameters.
if you really want, absolutely. Excellent question. So even with these original scikit-learn packages and functions, the hyperparameter tuning, you can actually change certain selections for an SVC, like the kernel check, the RBF that we did. There are other things that you could also modify and change to get a better
Polynomial kernel,
Polynomial.
other kernels, and also the C.
different, exactly. A lot of those things. And there are books that if you wanted to master just scikit-learn, you could do this with just scikit-learn. And you understand all of the mathematics and everything behind it. Yeah. But we're trying to go
Because my point is that maybe changing C, you can get something even with the limit.
Absolutely.
In
Absolutely.
the case of C equal 1,
Yeah. We're doing more of a journey here to try to cover a lot of ground. So we're going to get past, we're going to leave SVC behind, and let's try to do a K nearest neighbors. Same thing, I won't bore you. If you just do a K nearest neighbors, which is neighbors equals 3, that's one of the hyperparameters that we were just talking about, you get a fit like this. Not very clean, right? If you increase that to 25, let's look at this accuracy, went from 90.6% to 91.2%, but you can see it does a better job of classifying, just an unsupervised classification. It does a better job of classifying the data, right? So if you work in the biotechnology space, if you work with drugs or any product which has an algorithm or data-driven anything that you have to submit to regulatory agencies, the FDA, for instance, they don't want black box algorithms. A lot of the work that you do in biotechnology, for instance, that have to be submitted in these regulatory filings, those are considered medical devices. An algorithm is a class 4 medical device. And so when you submit it, they have to be able to see, and you can't just say, here's what's a model and here's what it is. You have to say a little bit more, so you have to kind of provide visual documentation, so on. Which is why in biotechnology there's a preference for decision trees and random forests. Why? Because you can, with those algorithms, you can lay out some sort of decision tree and you can depict it and say, I did a boosted decision tree for random forest, I've got 100 different trees, here's one of them, here's a picture of one of them, and you can kind of show how that works. That's why you'll see this pretty common in industry. So let's build a random forest. Same thing. Effectively, it's like a decision tree with a lot of different decision trees. And here's the output. You can see that because decision trees are if this is greater than that, you get these boundaries that are parallel to these axes in classification. Great. Now, yes.
Just to clarify, in all these models that you're training, so you're plotting how the classification plays out along these two features. Are you just using these two features?
And the left.
And okay.
Right.
Okay. I just wasn't sure if there was like a big other set of features that aren't.
No, we're just playing with the data.
Sure.
Really. So great. And even with this, there's a tool that unfortunately no longer works on my machine. It's called GraphViz, another funky package. It's not supported. It was open source, and like all open source projects, when somebody who's been working on it gets a better job or wins the lottery, they're no longer working on it, and it goes to the wayside. So this GraphViz has not been updated to support the new APIs within the OS 10 Mojave operating system. So I'm out of luck. I had some pictures with similar data set that I was able to get, and here's what it looks like. If I were to look at one decision tree. Go ahead.
Those previous graphs you had with the SVM, is that also using GraphViz or it is?
Oh, which one? Oh, these?
No, yeah.
No, these ran dynamically right away. No,
I
these
know,
are-
what do they run with? What is the?
Oh, this is just
Smart
within
SVM.
scikit-learn. It's just scikit-learn's whatever image graphing tool they call modeling tool.
Matplotlib.
Yeah, or Matplotlib.
Yeah, that's
It's,
okay.
I'm sorry, Matplotlib. I'm using plot. Matplotlib.
Where's that?
Plot, slim, so, thank you. These are Matplotlib plots. So this is GraphViz. Anyway, it doesn't work. So now, I don't know how long we've spent on this. This stuff can go long. I'm going to try to speed it up. Let's actually build some models. All right. We can select. And I've done this because taking the data that we have. This is what these are the columns that we've got. Actually, no. I did not run. No, I'm not going to rerun it anymore. We did the one-hot encoding, and that didn't carry out. I didn't run that, and so let's leave this as is. So when you do the one-hot encoding, and you split the data, and then we're going to, in this one cell here, it's got a lot of my notes, I apologize, but we're going to select to run certain algorithms with these hyperparameters for the classifiers, and just say, here's all those models that I selected, go ahead and run them, and then dump their results and print it. So if I were to run this now, this would take about 10 to 15 minutes, only because I picked neural net over here. And I want to throw it in there. So even if I run it, take a while, but here's the output that you would get, right? And so for this, I look at for the accuracies, I get the average accuracy, and the cross-validation, and the standard deviation. And you can see nearest neighbors does this. Naive Bayes, in the way that we did it, had 64%. Just to compare, Naive Bayes that RapidMiner did had an accuracy of 87%. By the way, it's almost done. Just like gradient boosted decision tree, SGBs. Pretty cool. All right, so we do that, and we do some additional statistics on each of those models, precision, recall, and so on. Folks, if you're ever going to need, this is important, go to Wikipedia. Just search for precision and recall. In there, you'll find this lovely little table that says what precision, recall, this, accuracy, and so on. I found this, and I've been using this since 2014. I have multiple colored prints, just one page of this table, and I have it in like every notebook.
What is that?
Just do a Wikipedia search for precision recall, and you go down to definitions. It tells you, so what it is true positives, true negatives, false negatives. And so when somebody calls power, what's power? Well, power is just the rate of true positives. False negative is also called a type 2 error. It's this, it's predicted condition false, true condition is true. So it's a false negative. And if you wanted to calculate what is a false negative rate, well, this is how you compute. And so all those key statistics like accuracy. Accuracy is sum of all the true positives plus sum of all the true negatives divided by the entire population. the trues divided by the entire population in this confusion matrix of predicted events. What's fun is when you go beyond confusion matrices, beyond 2 by 2. That's a whole new world there. So anyway, for that, we calculate some statistics and so on, blah. Great. So what we've basically done is what in the scientific world is called p-value hacking. We're just running all these models and we're trying to find the best fit because my data is just representative of the whole universe, right? And so that's all we're doing. We're doing all this stuff. Great. So that's what we do. Let's try the reality. I've got a function here, just thoughts, accuracies, and so on, just stuff that you guys can have. Let's build a random forest. And I've got code, Python code here that just says, okay, show me the time when it starts, how long it takes to build these things. I'm a little leery of doing it again because I know my data set internally is messed up now. And you get sort of the validation plots. And what you want to see in the cross-validation, over here I did, I think, 20, max depth. I did a depth on this decision tree of 20. And you sort of try to plot this, the validation curves, for the training and the validation, because I did do a, and you want to look at where the curves split. So I'm going to have to make this a little smaller. You want to try to pick the max depth at where they split. So here's 6, but when I look at it, I thought this is good enough, 9. So I tried to do 6 or 9. I did that to try to do cross-validation, max depth 6, 9, get output, get a plot of the accuracy results, and you can kind of see it does quite well, where with this decision, random forest with these parameters, for those who lead, it has an average accuracy of just right 86.5% or so in this range. And you can kind of measure the feature importance and so on. This is all, I should not have done that. Should not have shown those features. This is good, but can we do better? Could we do better? There's one other trick. What's called principal component analysis. We're just going to do a little survey here. For PCAs to reduce dimensions. So here we're, when we do that and we try to visualize how valuable each feature is to contribute towards the performance of the model, and you can kind of see that. You know, we're going really fast here. How's the best way I can explain this? For this, can we split some of these up and drop certain features that really aren't valuable? What are the things we could do? Principal component analysis, without going into any of the linear algebra with eigenvectors and so on, allows you to look at all this and sort of isolates. Here are the features that are most valuable, and the others that are not, so we can and you can concentrate them. Anybody have a better explanation for PCAs? Always struggle with that.
So it's dimensionality reduction, and it's based off of correlation. So your brain actually does this naturally. Like when you're looking at the TV's in 3 dimensions, but you're ignoring that 3rd dimension. You're only looking at the TV in 2 dimensions. That's because the most change, the most correlation is happening on those 2 planes. So PCA is just like a more mathematical, rigorous way to do that. Like you said, it uses eigenvectors.
I've heard it described as like, so if you have some data that's distributed in a multi-dimensional space, you rotate the major axes so that the first axis lies along whatever path has the most variance, and second axis lies along
this next best variance and so on, so you can cluster them in that space.
And each of those new rotated axes are the first, second, third, and so on, principal components.
Yeah, and so that's really all we're doing here, where here's the Python code that just says, for these select features that I picked discretionarily from my feature importance chart, reduce them. And And it does that and gives you the first principal, the first component, second, and so on. As you can see, this was written in British method, so I took this right off. And once you have that, you can create a whole new, another data set, and then you can build your random forest classification, which is what we did before, and look at how well that does. And as you can see, in this case, the same random forest classification model that we did above as our trained model, using our data set before we reduced dimensions and did PCA, and after. After is, most of them are above 90% accuracy. Compared to previously, it didn't even cross the 90% threshold. So clearly doing PCA helped even more, incrementally. Are we done yet? Are we done? Is that good? Can we just say, that's good enough? Let's just say that's good enough. All right, so very quickly, the mechanical stuff. If we want to build an operationalized model, when, like H2O calls it Mojo, the model optimized Java object, and so on. Everybody's got something. These are pickles. In pandas and scikit-learn, you save them as a pickle file. So here's the model that we had done. And for that model, with all of the PCAs and everything, let's build it with the entire data set. And then save it, do a dump of that model to a pickle file. And here's model governance for you. Track what you call it and give it a version, maybe even a date. The old school model governance from several years ago. Now, because you're using other packages, there's a versioning control built into some of those packages. That's all. So here it is. So now that we've got it, I can actually, again, Jupyter allows me to run a command line and says, yeah, do I have a PKL file? Yes, here it is. Or, list all my files. I wasn't do that, but whatever. Now that you have a pickle file, you can save that pickle file and email it to somebody else. Great. So you email that, and that person takes it, opens up in a Jupyter notebook, and does a job that load, and it loads the pickle file. Okay, great. So how well does this work? Let's create a person. Let's create Stephen Miller. Let's see if Stephen Miller is going to quit. All right. So we create the data set, and because remember that pickle saved model had to have those PCAs, because we use the PCA, right? That's a column as well. So the way you create a series object in pandas, because that's how scikit-learn works, you put in the values, and you keep adding those values, whatever, for this longer series, and the last one will be the column headers, right? And so, voila, I've created the Stephen Miller object. If I were to do a Stephen Miller dot type, it should say it's a series. Series doesn't have a type.
One question, right?
Yes, sir.
Just try to track it off. How does the PCA component have with it?
We just threw numbers in there. In this case, you're discretionarily putting something in. It's a very good question. If you were to operationalize this, you would then, and if you want to build a software out of it, then the software engineer is going to look at this and say, hey, you did this principal component analysis, that variable, how the heck did you create it? And you give them your code, and the software engineer is going to pull his or her hair out, saying, how am I going to recreate this as a transformation of taking available data and creating that principal component 1, 2, and 3, the first, second, and third, that I can then input into your version control trained model. Yeah, that's the hard part of software building, working with data scientists. Excellent question.
The sample data you had used earlier automatically generated multiple feature sets,
The
right?
PCA is based on
Yeah.
our run of the dimensionality reduction step.
It has its own way of doing that,
Correct.
while we did it manually.
Correct. And if you were to use a whole different package, we use scikit-learn to do principal component analysis. What if you use something else? What if you were doing this in R? You could do identically all of this in R. And R's doesn't have scikit-learn. R has something else. And you were to do principal, yeah, then you're using something completely different. Then you have Apple storage there. Nice.
How are you computing the one object code for the new person?
What's that?
One object code
For the new person, again, I know what those values are, so I will put those values in.
you have a lot of data.
Yeah.
I think you have to that's store.
Correct. So if you were to think, like, if you wanted to predict somebody, their propensity, the probability of leaving the company within the first 5 years, before you hire them, based on information in their job application, then yeah, you're taking stuff like this. You're saving this kind of data, and then you're going to run that. Here are the features of Stephen Miller. And okay. His salary was, initially I set it as low. I said Stephen Miller's salary is low. Let's look at a couple of things, like satisfaction level is 80%. His last evaluation, he got 85%. The number of projects, he's working 9 projects. Stephen Miller, he's got to save the world. Or change it. So 9 projects that he's working on, but, and so on. Right? And so here are all of those things. Now, all we're doing is taking that pickle file that we did, we loaded it as something called working model. So just run working model, predict probability for features Stephen Miller. And here's what you get, the 0 and the 1. There is 31% he stays, 68.6% Stephen Miller quits. Okay, what if we change a few things? Let's take him from working 288 hours a month. Let's let him work fewer hours. Let's take away some of his projects. If he can only work on 2, he works on 2 projects instead of 9. And let's give him a 99% on his job performance review. Okay? What would the predicted probability that he would leave become? Here you go. 77% he stays. 22% he leaves.
Salary is very low variable.
Salary does. I was playing with this. Salary actually for Steve Miller did not.
Is this representative of the data that they gave you? Because
On that train model that we did.
yeah, but is this representative of what a client would give you? Because there's some very, very key elements missing, like what is the age, what is the sex, what is the commuting distance to work, what is the square footage of the Home Depot store? Because if it's gigantic,
And that is a proxy for value of a house and income level and so on. Proxy further for zip code. And zip code is the most predictive feature of whether you're going to get good care at a hospital and whether you will be readmitted to a hospital within 30 days. This is coming from a major insurance provider.
that makes sense.
So,
So
I mean,
you could
profiles.
have cases where the client gives you all of this data, and they left out fundamental elements of the data which they had access to but didn't think of. And it's now your job to start this kind of endeavor.
But if you think about it, gender again, right? But if you can increase the salary or enhance satisfaction,
You might only have to change it for one gender and not the other
Is this
to get someone to stay.
reality? This is like they
are
This is like data.
profiling, right? So-
Well, you let the data tell you the truth, and then you decide how
I
you
work
want
with,
to act on it.
I was one of those scary people with scary access to human resources data, all access. I had everything of everybody, including their, and I could get their blood type too if I wanted. And if I look at things such as the gender differences in pay scale, women are underpaid, but women are only underpaid up to a certain level. When you reach a certain level and title, you are vastly overpaid over your male counterparts. Become a leader in an organization, in a company, you'll be vastly overpaid.
Okay, I'll put that. Just go back to this. This is data. Okay. Now that I understand.
Yeah.
What kind of workers are these? Sales guys, right? Sales guys.
You saw the departments. One more
So
question.
they bring up a really good question.
Yes.
So thinking about things that might help your ability to do your job, which would be to predictive analytics for when an employee is likely to leave the company, or if this is going to be used for hiring, can you even use things like age and sex, or is that biased? Right.
You'd have to test for
Can
bias.
you incorporate race, or would that be unethical?
Ethics is an entirely different matter.
Is this for all levels in a company, or is this a
This is just a data set. This
a
is just
sample?
one sample
This is
data
a
set.
sample. It's not 15,000 employees.
Yeah, it would always vary. If you wanted to do this, and if you were given like HR strategy, figure out a way that I can keep my people. This is also the stuff with econometrics. One of my close friends, PhD kid, University of Chicago, so I know all the economists. Susan Maffei, who won the John Bates Spark, which is always a predictor of the winning Nobel. Susan is hopefully, she thinks she's going to win the Nobel Prize. She's focusing all of her econometrics work on machine learning. For that, it's applying economics on the concept of counterfactuals. When you do these sorts of predictions, what part of it, what does it really tell you? And if you broaden that, what are those actual levers in society that say this is a salient trend in all of society?
Because it doesn't seem normal to me that somebody that wants to work less hours or
Well, there are all these other dimensions as well, right?
It just
Those
seems-
other features.
people only change a couple variables.
We only change a couple of variables,
Yeah,
and
so
it
variable
alters
one.
their propensity.
It doesn't
But
make
that is
sense.
based on the trained data. The data that you had showed something. Of the 14,999 people, 15,000 minus 1, people that we had, whose records that we had, those are, you're only saying, of those who actually left and those who actually stayed, can you find a predictive function that explains that data set? Is it real world? No.
But we're trying to get to the real world.
Then you get bigger and bigger data. Data is the new oil, right? You need more and more data because we have the computational capability, and you need more and more. Yeah. This is just a sample, and it's very specific to just this company.
Nash, one very quick question.
Yes, ma'am.
The figure file that the final model that you were selecting now to classify Stephen's probability. I know you ran multiple models. I probably missed that part. Did you select one model to go
I
forward with?
picked
or is it
one
going
model,
through?
right here. I picked one model, which was the random forest classifier with these max step 6, number of estimators, this, and I saved that, and I ran it with and did a fit on that for everything, and then I saved that operational model, saved that as the file.
Is there a way in Python where since you ran multiple models, is there a way that we can still, when you're trying to classify this new entry in the data,
Save them all.
to run through all of them?
Yeah, that would be
You could do
interesting
a
to see.
for loop map and so on. Yeah, absolutely. Yeah.
That would be interesting.
I couldn't do that right away, but give me some time and I'll just kind of like fudge my way through and hack my way through into exactly that. So, yes.
I was able to find the answer to what the variable number project for this particular project meant. So it's the number of projects completed in an entire time the employee was at the company, not at the moment.
Not concurrent project.
So kind of makes more sense when I start to think about
That
how
would be
it fits in the context of the project.
Yeah. So in that case, if it's a number of projects that the person has done over their tenure, that would be a proxy for their tenure.
Okay.
How long they've worked for the company. More projects.
Do you have any opinions on? I didn't let you finish. If you had a comment or.
They must be bored or something. They like being bored.
Right. I'm interested in the talk about the ethics thing. I don't know if that's a long
Can we
conversation.
table that? Because I'd like to go through,
Okay.
yeah, we'll table that. This question around the ethics, we'll see how much time we have. We'll come back to that, I promise, if we have time. Let's get to H2O and rapid miner. I did see someone from H2O here. I don't know if he's still here. But this is H2O's open source tool. And so what we did was run it. H2O, remember, if you recall certain things like Kuba said, H2O keeps data frames as these hex files. So you have to import in a certain way. So import it. Here's how, take a look at it. It's the same. And what I did was I imported that same, not the pre-processed data file, the original data file. No, it's got is smoker. It should have is smoker. And already figured out that's a categorical variable, lay it out. Yeah, H2O does a lot of these things, even the open source version, very, very, very well. And then I'll change it to categorical, so I can say it's a numeric versus categorical fields. It's important that I tell H2O that left, even though it's zeros and ones, that it does not look at that as a numeric field. But otherwise, in that case, it's going to do any kind of model that I have it run, will do a numerical regression. I don't need regression, I need classification, 0, 1, right? So make sure it knows that. I removed is smoker here, and I kept all of them, all the others. Then I create train, validation, and test. And call AutoML and run it. This whole thing, AutoML function, it runs it, and it does give a model ID, H2O's own data model governance. As you can see, it puts a time date stamp on the type of model, and it gives a numeric number to each of those models, because it's trying everything under the sun that you throw at it. This open source version of H2O has XGBoost, which is what wins all casual competitions, AutoML, and various other core algorithms. So we run this. Like I said, this takes about a couple of hours or so to run everything. I picked the leader model, the one that has, and I have it sorted by accuracy. What did I say? No, I guess by default it'll sort by accuracy. AUC, not accuracy. It sorts by AUC. We'll have to look up accuracy. So based on that sort, here's the leader, which is the gradient boosted machine. And that one has on the training data, you can see the confusion matrix. And so on the training data, it has an accuracy, max accuracy of 99.8%. On the training data. Obviously that's overfitting, but let's see how it did on the validation. The validation had 98.9, a little lower, okay? You don't want it to be the exact same. And then cross validations, you can see how it does. I know it kind of bunches it up. This is what you get for free. But you kind of get like, okay, it does 98.7 average. Here are the metrics. Here you go. It's a mean. The mean accuracy on cross validation is 98.7, and AUC is 99.3. Scoring history, everything. So now that we have, and you can see the feature importance. It did not create any funky features. It left the features as we had it. Satisfaction level was the most important, followed by time spent per company, last evaluation, and so on. We can compare and contrast this to go above the scikit-learn version of feature importance. We'll come back to that. And then you run the test on it, you get a performance, and you get a plot. As you remember, on the test, its area under the curve is 99.2%. So this is a really, really good model. This is a model that's too good. You don't want this stuff. And it just happens to me. If you found that data set, yeah, this is one of those public, it shouldn't be this good, but yeah, it is. And done. What I did was, I tried to see, well, what would if I were to run this on the entire, no train test, I just did it on everything. And I think it still, did make some changes. It didn't do much. So now that you've seen this version of H2O, H2O alongside, when you run it, and you'll have seen this in Kuba's sparkling water presentation, when he ran H2O, he showed you, there was a IP address that shows with :54321. You can get all those pictures online, honestly. That, when you go there, that gives you what's called H2O flow. And the H2O flow is like, it almost seems it's a web app of the H2O engine. And so here, I can call, it's like a little program. This is part of that same free H2O package that we were running in Python. It also creates a web server to localhost to your machine and then allows you to access the web app front end for that same H2O engine that we were running. And here, what I did was I just said, okay, let me take the updated, that HR data. I called it this. Here's the table. And let me do another run of AutoML and see how long it takes. Well, that one took a while. Here. Build a model, and so on. You can do all sorts of funky things, PCAs. It allows you to do some very, very cool things. And this is just H2O, what they freely make available. You can do just principal component analysis, and so on. All of that's there. Now,
how do we know if PCA is a good fit for this data set? Because sometimes it can and can't be.
Work with it. You just have to, honestly, paper and pencil and just plot it out. Here's the kind of results I got. And take notes and then show somebody else a second set of eyes to say, here's what I'm seeing. Here's the kind of pattern I'm seeing. When you're trying to figure out if this is a good fit or which good model, or is it PCA a good thing to do or so on. Write it up, share it, and get it peer reviewed is the best way I can put it. So now let's flip over to RapidMiner. And with RapidMiner for accuracy, can we do AUC? We can do AUC as well. And you can see AUC for the different models, it did this. Just to compare and contrast, let's flip over to H2O. The leader model was a gradient boosted machine, had an AUC of 99.3. RapidMiner, a gradient boosted decision tree, 99.2 AUC. Now, let's go into things such as, for deep learning, I hate deep learning, decision trees. Let's look at the model. And here you get, here's the decision tree model. That GraphViz thing that I wanted to map out, well, I couldn't get GraphViz, obviously open source tool to work, but within RapidMiner, here it is. And you can kind of walk through the tree, the satisfaction hours to a number project, and then splits into average monthly hours and satisfaction. And it actually, here's something else. Even in the decision tree, if you look at the feature sets, look what it did. These were the features that it created. So it took average monthly hours, but it creates new ones. Okay, this one it did not. Some of them they do. They'll create new features sometimes. Did I get that? Where it is basically, when they say complicated, the feature engineering is things such as promotion last 5 hours multiplied by the log of last evaluation. Square. Like, who's going to come up with that? Which human being actually comes up with that? Because I want to know how that person is. That person's really, really smart. This is what the machines do. When it does end up, Dr. Ingo, the founder of RapidMiner, his thesis, his doctoral thesis was around these sorts of feature engineering. If you look up his papers and so on, he goes into the mathematics and the mechanics of how you do this. He took that work, made RapidMiner. No different than 30 years ago, Stephen Wolfram, one of the smartest guys on the planet, he took his work and built Mathematica, which is still to this day one of the best mathematical software tools out there. One other thing, you're going to love this. We talked about H2O. The deep learning, it did a deep learning. We looked at the performance of deep learning was, 97.7, not always the best. But if you look at the deep learning model, scroll all the way down, what does it tell you? RapidMiner is using H2O's deep learning module. Which one? Overview, or see, this one? Oh, the overview? Yeah. I actually, I didn't know if this was going to work, so on my PowerPoint file, I can share this. What I did was I actually took screenshots. And if you guys ping me, I will at least get the PowerPoint doesn't have right away. Just message me on, give me your email address on Twitter. I'll send this over. I'm doing on time. I promise you.
Is this data set, is this the modeling? Is this indicating that precision or the deep learning is the most accurate?
No. This is
telling us?
This is the best way to look at it. Compare and contrast. You can see for yourself which model does the best, and it's usually XGBoost, gradient boosting. This last one, 99.2.
So those two trees?
Yeah, the gradient boosted trees.
So that's
XGBoost. And XGBoost always wins, like Kaggle competitions and so on. And you can call it, you can run it, Python code, R code, whatever. Here's the thing, you keep playing with that. Yes, they win Kaggle competitions, but is that something you can run a company on?
Kaggle, you mean like
Kaggle competition. Sorry, Kaggle is a competition site. It's been acquired by Google because Google wants access to people's code and models and insights and so on. Kaggle is if you haven't got a Kaggle account set up, please go set it up. It will give you access to data. It will give you access to other people's notebooks, code, learning resources, tons of stuff. Everything to master data science. You can do this for free. The computational, really heavy computational power, whatnot, you can pay Microsoft or Azure subscription, and I'm happy to set you up, and you can pay a few $1 million a year, great, or you can do it for free. However, if you're a publicly traded company, your board of directors will not like that, and they'll say, no, you've got to pay.
And you would use Kaggle for that?
Kaggle is just another platform. Yeah, Kaggle is everything.
Are any of these for a particular business case? Or is it good for all? Like,
It depends on what you're building. There's so many different software packages, methods, and approaches that you can do. I showed you one. I'm going to be presenting this. I presented this to one company, a steelmaker, and I'll be using a variation of this with the chief of strategy for a major bank. So, gonna go see him soon. Maybe next week. But that's other models, other things I've done were completely different. Blue Cross Blue Shield model is completely different. Subaru, the AI, predictive intelligence built into their engine assembly that I built by hand, completely different. The predicting patients with rare cardiovascular disease, that was as you can imagine, it's a decision tree, very complicated with EHR records. So you're going to have a lot of different ensemble models. And so H2O does a really good job of building ensemble models, by the way, out of the box. Which basically says you're taking your data and splitting it into different chunks of it, building different predictive functions for that, applying that, and then bringing it all together.
that's how it works.
Is there any advantage to use Python, pure Python, against these tools, RapidMiner,
Is a really good question. Is there an advantage to doing everything in Python versus paying for some of these additional tools? The tools make a lot of your work easy. My premise from this talk is if you, as a business, you don't have to spend a considerable amount of money on expensive consultants like myself or data scientists and so on. Data scientists are analyst level jobs. They are what your college level analysts are, and you pay them just as much. You don't need people with that, you need people with domain level experience. So this stuff that we did with HR, this is stuff that your human resources directors, human resources managers in your corporate environment, they're the ones who should be doing this. So in the world that I come from, companies like Home Depot, GE, and all that were very Six Sigma oriented, if you wanted a promotion, nobody was going to give it to you. You had to do a Six Sigma black belt or green belt project. You have to demonstrate process improvements of a certain amount. Various companies like Johnson & Johnson, others have things like that. If you do that, then you qualify for a promotion. So, and that was a way to change the culture of your company to be more data driven. I'd love to be able to see more machine learning ninjas out there. It doesn't matter if you're working in IT, it doesn't matter if you're working in operations, it doesn't matter if you're working in human resources, you should be doing this. Do this, for one, it's job security, but for others, this is what you're supposed to be. If you're not, then you're dead weight in an organization. Period. And everybody across, up and down, need to be doing this. That's my opinion. Take it with a big grain or lump of salt. Any questions? Ethics.
Yeah. Mainly like, is it a data scientist's responsibility to worry about that?
Yeah, so I was talking to Gary Mendel. He founded an organization called Shadow Group for combating battling addiction. Great organization, folks. Gary, who was a prominent CEO of a major organization himself, he lost his son to addiction, who had battled addiction, to his own life. Gary then launched Shadow Group. I've been trying to convince, having conversations with people, telling them that, look, I can predict people before they have an addiction event. Because forget cancer, if you take all the medical conditions, you add it all up, they still don't come up to the number of fatalities that we have from addiction today. If there is something that we can do about it, we can. Now, why I say this, I believe in my heart of hearts we can build it, and here's the kind of model I wanted to use EHR records and so on to build this training model. I talked to one of the major, the number one accounting management consultancy, whose name gets dropped all the time. Their nonprofit group is already working with the leading social media company. And they've already built trained predictive models for predicting when somebody is going to have an addiction event. That data comes from social media feed. You can't publicize that you have it, but it's there. If you work in pharma, biotech, there are a lot of things that we built predictive models to say if somebody has a rare cardiovascular disease. This is human life. They can't do anything about it because if you know it, then you have a responsibility to save someone's lives. Now, if you're a publicly traded corporation, you could save a human life because you got this capability. You better not spend any more dollars in improving that capability. You better shut that thing down. Because if you're not helping to save human lives, then you've just added a major liability to your corporation. So certain organizations have access to all this data. They do play with it. People like me, yes, we do play with the data that we have access to. But you never, ever do anything. If it's not mandated, then it's not part of your job. You shouldn't be touching it.
Have you done the stock market?
Yeah. I can't talk to that. Yes, I work for a hedge fund. I'm trying something else. I come from the stock. The thing with stock markets is you can build great models, but very few people make money. Ray Dalio with Bridgewater, he's pretty much taken his entire trading floor, and it's all algorithmic based now. Revolution, there are a few firms before. D.E. Shaw was the first one to do it in the late 1970s. One of D.E. Shaw's own favorite analysts straight out of Princeton was a gentleman named Jeff Bezos. And Jeff Bezos built that, he worked on those things and he did quite well. And he left before D.E. Shaw crashed. And D.E. Shaw himself tried to convince Jeff out of like leaving the company on this stupid dream of like chasing the internet to make an online bookstore. Just yeah.
I mean, just back to the
Yeah.
ethics on that, you know, that in the
Yeah.
stock market,
Well,
potentially.
Stock market, anything goes. In finance, not anything goes. Do whatever the heck you want.
It's like insider trading because I have this knowledge.
Oh, there are laws against insider trading.
No,
But
I
what
know,
you
but-
can do is high frequency trading. So high frequency trading is can you get certain signal before anybody else and you're trading on nanoseconds. And that's been done that's been done like 20 years. I mean, Liar's Poker guy, Michael Lewis wrote a great book on it. It's a great book.
I would say that actually quantitative is at an apex at the moment. More dollars have flowed into quantitative hedge funds than fundamental hedge funds in the last year. I think they manage over $1 trillion in assets.
Oh, far more. But it depends on which firms. Like Bridgewater is, I think.
Two Sigma is another big one.
But here's the thing. For us as economists who work in this space, so I was one of Gene Fama's kids. Gene won the Nobel 3-4 years ago. He coined the words efficient market, right? And I worked for Dick Thaler, who won behavioral economics. All of that body of work, the financial economics research work that we've done, are based on discrete time events. Day, closing price, or so on. And we've tried to predict these things. In a world where you have every precise movement of every equity around the world, Gene would tell you, Fama would tell you that efficient market means the market is everything putting the shirt on your back, right? So if you're working and you've got data, real-time data on every stock price around the world and every tick by tick, and then you try to find the trends, the salient models and so on, the economics really are very different. All of this stuff that we talk about, the capital asset pricing model and so on, a lot of that can probably be thrown out. So a lot of traders will try to build pairs, trading covariance matrices and so on. Good, but good luck making money. Very few people are able to make money unless they have a significant mechanical competitive advantage, like they are able to get certain signals before everybody else. And they're able to fine-tune their models on a dime. So it's a combination of a really smart trader with experience with, well, I don't want to call this AI, but yeah, this stuff, whatever you want to call this stuff, this kind of machine learning. Let's just call it machine learning. So it's a human being with machine learning. That's where the true power comes. And so you take a physician, a radiologist. I wish our radiologist friend was here, Dr. Steven. He's one of the few radiologists in America who also codes. And he's got a big practice too. You can't take him out of the equation. I think there's a keynote session about radiology and
tomorrow.
Yeah. I don't see how you can take him out, but you can take him and give him these tools of image recognition and make him faster and better. I think I am out of time. I hope I have at least had a chance to turn you guys into data scientists. So you are empowered, go change the world. Do a better job than Stephen Miller.
Yeah. He doesn't like projects.
We know that with you. And we don't want him to learn projects. I'll shut up with my politics.
Thank you.
Stephen's a friend of mine.
Slides.